Welcome to class. Today we'll be talking about continuity and the intermediate value theorem. Continuity basically means that the curve of fx is not interrupted and has no hole. Mathematically, it can be expressed through this equality, such that the limit value of fx when x approaches a is equal to the value of fa. It makes sense because, as we have learned earlier in Module 1, the limit value of fx corresponds to the approaching neighboring values. Now, if the value of fx at x equals to a does not match with the neighboring values, then a hole in the curve, and the function wouldn't be considered as continuous. Here are some examples of discontinuous functions. In the most left one, there is a hole in the curve at x equals c, as fc is not defined. The limit as x approaches c does exist, but the function is not continuous. In the second case, the graph in the middle, the limit value is not the same as the fc value, so the function is discontinuous by definition. Also, graphically, there is a hole in the fx curve, as in the first case. In the third graph on the right, there is a jump at x equals c, so limit does not exist, and the function is not continuous. Here's a summary of the types of discontinuity. There are removable discontinuities, such that the curve is largely continuous, except for there being one or more holes. Then there are more serious discontinuities, such as jump, infinite discontinuity, and oscillating discontinuity. The fundamental difference between removable discontinuity and essential discontinuity is that in the former, limit exists at every value, yes, even at the holes, while in the latter, limit does not exist at the place where there's the jump or where infinite or oscillation occurs. The intermediate value states that for a continuous function f on the closed interval ab, and for any number, let's say n, between the values of fa and fb, there has to be a number c between a and b such that fc equals n. Basically, it says that since the function is continuous and the curve has no hole, then as the y value goes from fa to fb, all values between fa and fb has to be covered as x gradually varies from a to b. Let's do one problem that utilizes the intermediate value theorem. In this problem, it wants us to show that there is a root, meaning an x value that satisfies the equation of root 3x equals 1 minus x. How do we do such a problem? Here, we can set up a function of y which equals root 3x minus 1 plus x. So finding the root for the equation is transferred to a problem of finding an x value that will give a corresponding 0 y value. So we can arbitrarily try out some x values to see what kind of y values we get. If we manage to get both positive and negative y values, then we can conclude that there must exist an x value that will make a 0 y value, as 0 is between positive and negative numbers. So let's try. First, let's try x equals to 0. We pick 0 just because it's easier, algebraically, easier to calculate. We wouldn't need a calculator for that. So f0 gives us negative 1. Then we try another very simple, a special number, give very simple algebraic operations. So f1, x equals to 1, gives us 1. So here we have both negative y values and positive y value. So we can conclude, based on the intermediate value theorem, that there exists a value x between 0 and 1 such that fx equals to 0. and this particular value x is the root for the original equation. So this exercise shows us that sometimes we need to rephrase a math problem in order to apply certain theory or use certain tools. Finally, I would like to share with you a poem written by myself actually, Continuity versus Discontinuity. I hope you enjoy the poem, and I hope you understand the concept of continuity and types of discontinuity after watching this module. Goodbye. Happy studying.